which is Frantisek Ruzicka from Nuclear Physics Institute in Rzesz, who will be speaking about something which was addressed a year ago. Pseudospectra in quantum mechanics, please.
Yeah.
Czech people here are admiring the Czech apostles.
Yeah. I think that they print it out nicely. It's like, yeah.
What is the text symbol for doing this thing?
What do you mean actually?
Text. What is the text?
Ruzicka. Yeah, it's like.
What is the text? How do you take it?
Yeah, like, well, as long as you have Czech installation, there's no problem. So, yeah, it's no backslashes actually.
It's very difficult in text.
Yeah. Well, so sorry about my name, maybe.
It's not your name, it's pronouncing
Rzesz is like, yeah, like Antonín Dvořák. Yeah, very little people who are not native Czechs can pronounce Rzesz. It's like, yeah. So we can start. Okay. So thank you for coming and thank you for all this conference and
Thank you for microphone.
I think it's working.
Yeah.
I think it's working actually. Yeah. So maybe I should.
It's okay.
It's okay. So finally I can start my talk, which shall be about pseudospectra in quantum mechanics in general and pseudospectra in quasi-hermitian quantum mechanics in particular. So, like a motivation picture, I included this one. Pictures like this we will see a lot throughout this presentation. I will explain shortly what this means. These are actually contour plots of the pseudospectra of some linear operator, and we shall be interested in the physical interpretation of these kind of plots. No, that's not an optical illusion. It's.
No, I'm saying it appears to be tapering.
Yeah, it's. Yeah, half of. No, okay. So we'll start with discussing pseudospectra in general in mathematics. Then we'll switch to discussing pseudospectra of Schrödinger operators, and at last we'll discuss. We'll address two arguments about pseudospectra in quantum mechanics and for quantum mechanical observables. So at the start, most of you are probably familiar with the book I'm showing here. It's from Le Trefetin, which is a collection of some 40-50 chapters, quite unrelated, which all discuss application of pseudospectra in all diverse areas of physics, mathematics, and numerics whatsoever. The basic definition which we'll be using is shown here. So the epsilon pseudospectra of a linear operator is just the resolvent norm. Actually, the region of the complex plane when the resolvent norm is larger than some given value. And here I just copied some chapters from the actual book to give you a taste of what pseudospectra can actually be used for. And if I should make a general statement what these things have in common, well, it's already in the book. It's the thing that all these things have something related to non-normal phenomena. As an example, to give you a taste of what pseudospectra actually are, we'll discuss first this nice plot. It is actually a plot of a circulant matrix. The circulant matrix is any matrix which has this form, which is block diagonal, and the entries wrap like anti. You see what I mean. They form like kind of periodic boundary conditions. Well, that's kind of nice matrix, and we can also associate, of course, a symbol to any of these matrices, which concerns the combination, some combination of the coefficients. Well, and then nice theorem has been stated, which claims that we can express the spectrum of such a matrix in a very nice form. We can express the spectrum in as the image of the unit circle of such mapping. And well, here I have shown the spectra. These spectra are the black dots. The matrix is taken of dimension 100, and the symbol is taken like I'm showing here. And the pseudospectra are actually the colorful lines around here. And maybe I should comment of what they actually are, because I chose not to include the actual size of the resolvent at the contour, because it's, for our purposes, it's not really relevant. For our purposes, the shape of the contours is relevant. So you will see just the contours throughout the whole presentation and no values at them. But just forget about the values and think about the lines as regions of the complex plane with constant resolvent norm. That's it. And so we'll see that the resolvent norm behaves quite nicely. It like wraps around the spectrum. And so now we can consider a Teplitz matrix, which is a more general one than the circulant one. You see the general matrix printed here. It's also constant like diagonals, but now it has not to have the periodic kind boundary conditions. So we can take essentially the same symbol as before and try to plot the spectra and pseudospectra as before. Now there is no beautiful theorem concerning the spectra, not at all. The spectra are forming a sequence of lines in the complex plane, but the pseudospectra are of the same shape as before. So that's maybe the first impression that the pseudospectra of some matrices may be revealing some information we might be losing otherwise. And yeah, because pseudospectra are generally they originated as a numerical aspect, so I should maybe comment of how I am computing them. So the computation methods are basically based on two equivalent definitions of pseudospectra. The first one, which is shown here, is that you simply take the matrix and you plot the eigenvalues of arbitrary number of random perturbations, which are smallest norm than the given value, and you arrive essentially at the same plot as before. Now the previous plots are all based on the contour plots of the lowest singular value, which is a quantity which is numerically quite possible to compute. The resolvent norm is not. And actually what we saw in the pictures may suggest a kind of a theorem which concerns the relationship between pseudospectra and normality, and such theorem indeed exists, and it has a very simple form. The theorem we state the theorem in this way, and the theorem states that the pseudospectra are always, the region of epsilon pseudospectra is always larger than the epsilon neighborhood of the spectrum of a given operator. And it actually coincides with the neighborhood if and only if the matrix or the operator under consideration is normal. So we have some quantity which we can compute in principle, and which will give us new information in every example of matrix which is not normal. Matrix which is normal, like we saw the circulant example, there will be no new stuff essentially. But for normal matrices, we can plot the pseudospectra and look at them and actually acquire something which could be of importance. Now, since we all concerned about quantum mechanics, that the natural question would be how would pseudospectra like for the common non-hermitian Hamiltonians which occur in quantum mechanics. And this question dates maybe to Brian Davies, who in 1998 was thinking about harmonic oscillator, and he took a simple harmonic oscillator which is simply a rotation of the usual Hermitian harmonic oscillator. There is nothing unusual about him, and the spectra can be computed very simply by a simple translation argument. But as long as you plot the pseudospectra, you may be very, very surprised, because pseudospectra of the actual Hermitian harmonic oscillator form circles around the spectrum, like the theorem says. But here we have pseudospectrum that blows up to infinity for high energy, so that could be potentially catastrophic if we try to assign some application to this operator, and that this actual method was taken again, was taught again by Krejčířik and Siegel, and again by Novak very recently, about 15 years after Davies. And they thought, well, if the imaginary harmonic oscillator behaves like that, maybe we could try to plot the pseudospectra for the imaginary cubic oscillator. The cubic oscillator has real eigenvalues, but we have not seen the pseudospectra, what they look like. And well, if you plot the pseudospectra again, you will see the same pattern as before. The eigenvalues are again safely real and bounded from below, but the pseudospectra blow up to infinity, and that leads, if one considers the operator like is in these settings, it leads to very, very surprising conclusions. I just quote two sentences from these articles above, which say that pseudospectra are proposed to play central role in PT or pseudo-Hermitian quantum mechanics, because they tell us about some instability of the operator, and then non-Hermitian Schrödinger operators have generally they have considered more examples of these operators, and they say that they have generically the wild pseudospectral properties. If just to emphasize the plot I was showing before, I plot it again now in 3D. So you see the Resolvent norm, like this is the real axis, and the Resolvent norm blows up for every eigenvalue to infinity. That makes sense, but it blows up as the real values go to infinity. It blows up in this direction. So that leads to the conclusion that high energy eigenvalues are unstable. That arbitrary small perturbation can put them very far away. So that's.
So can I ask, when
Yeah.
you say arbitrarily small perturbations, you are measuring it using an L2?
Yeah, this time yes. Actually, I will be concerning about that. Actually, yes. I know what you mean. So, yeah. And now it's time for me to review general mechanism of quasi-Hermitian quantum mechanics, but it was very beautifully done yesterday in the talk of Sergei Kužel, so I just review some small parts, because I shall not use the general Krein space formalism. I shall use the original formalism of Scholz-Gerhane from 1992, which says that as long as you have a quantum observable, well, this theory is firmly based on the ground that the operator quantum observable, that must be Hermitian. That's based on arguments, not real. It must have real eigenvalues, of course, but it's not enough. You must have also unitary time evolution, and that's a really physical argument which you cannot skip in any way. So and if you have unitary time evolution, you must necessarily have Hermitian Hamiltonian. So as long as you want to take Hermitian observables, quantum observables, they must certainly be Hermitian. But you can describe them like a representation by non-Hermitian operator, but you must make them self-adjoint in some other Hilbert space. And the reason to do this is that the operator in the non-physical Hilbert space may have maybe more simple. It's the imaginary cubic oscillator may be a prime example of such operator, because it has very simple form, but as long as you try to shift, I will get to that later because it's not so simple, to shift to physical Hilbert space, it would become very complex. And the two physical Hilbert spaces here are considered because you have actually two methods to make the operator Hermitian. You can either redefine the cats or define the notion of Hermitian conjugation. These notions for redefinition are equivalent, and those spaces are essentially the same. They are unitarily equivalent, and it's up to you which one you choose. And it's generally more easy to work with this space when you change the Hermitian conjugation, and you then the condition of hermicity acquires this form. When theta in the framework on Scholz-Hane, the theta is a bounded operator with a bounded inverse. So that's a generalization of the notion when theta is 1 and you have usually hermicity. Now we have to establish some equivalence or some relation between the quasi-hermicity and the pseudospectra of such operators. And it turns out it's very simple, because the essential theorem dates back to 1960s. And it really turns out that the Hamiltonian is self-adjoint if the epsilon pseudospectra is actually equal to the epsilon neighborhood of the spectrum. And now, as long as you have the pseudo-Hermitian or quasi-Hermitian Hamiltonian with theta and theta inverse bounded, well, you can transition easily to omega and omega minus, which are similarity transformation, and you might choose the constant defined like this, and the pseudospectra are satisfy this inclusion, which is quite trivial, and many authors consider this as definition of trivial pseudospectra. That means that epsilon pseudospectra is contained in some larger kappa epsilon circle, and you can essentially control them in this way. But and we have seen that already yesterday in the talk about unbounded G symmetries. This reason is really not enough, and we must transition to more general framework. Here we provide just some equivalences of which are not really commonly appreciated, but all these notions are equivalent with the quasi-hermicity, with the usual quasi-hermicity of the Hamiltonian. And, many of the notions are based in mathematical monographs, and the authors don't really know that this is equivalent to quasi-hermicity. And yeah, I just talked about that we must consider theta or theta inverse unbounded in some cases, and this mainly because we are having physically relevant observables. Physically not relevant, interesting is a better word, because, and prime example is already again the cubic oscillator, which we show that does not obey the condition of having bounded metric with bounded inverse. And so people have been considering the framework of having theta or theta inverse unbounded, and the results of this. And the complete theory is far from being finished, and we have some partial results, I can mention some which are found in this paper in Antoine Trapani, and particularly interesting that if we have theta bounded, but it has not have a bounded inverse, so that's quite a generalization. Then the point spectrum of the Hamiltonian is necessarily real. We don't know anything about continuum spectrum, but that's quite a step forward. And however, this negative result was shown some time ago by Krejcíř, and it says essentially that if we consider theta and theta inverse unbounded at the same time, we essentially couldn't get nothing new, because every operator whatsoever we choose, densely defined, can be made quasi-hermitian with such a matrix. And here now we show that actually for this framework of not having both theta or theta inverse bounded, we can make some very interesting computation which were started also by Brian Davies in the same year. And it has its roots in semi-classical analysis. And the actual theorem by Davies goes as follows. You have a semi-classical operator of this form, and you define a set which you call a semi-classical pseudospectrum, and which looks like this. And then you have a theorem that says that for every possible value in this semi-classical pseudospectrum, that it belongs to the epsilon pseudospectrum of the actual operator for epsilon sufficiently large. And this result is only for semi-classical operators, but we know about the correspondence between semi-classical limit and high energy limit. So people have been, and actually this is also a result by Krejcíř, people have been rescaling the Hamiltonian so the theorem can be applied to not semi-classical Hamiltonians, but actual Hamiltonians without the free parameter. And here I include the method for actually again the cubic oscillator. And it turns out that you compute the semi-classical pseudospectrum as this, and you actually get a region which is unbounded and which is schematically shown here, and which lies in the epsilon pseudospectrum of H. And this is like a conclusive proof, analytical, we don't have to plot anything, that the pseudospectrum is unbounded. We have an unbounded region which lies inside the pseudospectrum. And this, if the operator had actually bounded metric with bounded inverse, this couldn't happen. So this is a proof which actually was used in the seminal paper demonstrating that the metric operator of the cubic oscillator is not at the same time bounded and with bounded inverse. Here we include some other examples to demonstrate that this behavior is really generic throughout the Schrödinger operators with imaginary potentials of any kind. And in the case of imaginary cubic oscillator, the metric couldn't be found explicitly, but in this time we can find at least one metric explicitly. It's of course unbounded, and using the same arguments we can actually show that any metric whatsoever we can find is unbounded too, or with unbounded inverse. And now in the like section I'm going to make actually two arguments which are quite unrelated to each other, and the first considers discrete models. And when I was thinking why to make a motivation why should we consider discrete models at all, that I thought that firstly when you plot something numerically, you essentially have to use finite metrics. So all the plots you have seen before, they have been used with discretizations of this continuous operator. So if there are some discontinuities or stuff like that, the plots couldn't be anything near the reality. But actually the discretization of the operators have quite a success for pseudospectra, and this is based on the general property of pseudospectra, which is essentially continuous with respect to any possible notion of convergence you can imagine. So if you have some operator, some sequence of operators converging in norm to some limit operator, in basically any notions of the generalized convergence, then the pseudospectrum would converge to the limit, to the pseudospectrum of the limit. Another reason may be that we actually have not a complete understanding of quasi-hermitian Hamiltonians in finite dimensions. It's not the case like for Hermitian Hamiltonians, where you can parameterize the matrices without problems. And actually, when we differentiated these operators, the most efficient methods that could be used are shown to be spectral methods. They are more efficient than some finite differences or finite elements. And still the convergence is quite slow, as I show here. This is eigenvalues of the spectral discretization of the cubic oscillator for dimension 4000. And the actual real spectrum is just the first part here. Now we will actually demonstrate the usefulness of considering finite dimensional models into two examples. And first is the discretization of these well-known models introduced by Krejci, Riegbela, and Znoil, which has the form of Laplacian on a finite interval with Robin boundary condition, which look like that. The discretization, equidistant discretization, shows to have this actual form. And now, as long as you want to gain some insight into the finite dimensional operators, you can construct the metric operators, because in infinite dimensions it's actually quite a big problem for many operators to construct even one metric operators, and we know that they are infinitely many in the L2 space, and actually there are n free parameters for metrics in n-dimensional Hilbert space. So we can proceed by constructing a set of pseudometrics, which are essentially metrics without the conditions of positivity, and which we try to find some pattern which spans to arbitrary dimensions. And if we are lucky, we find that one of the pseudometrics is actually a matrix for some parameters, and we are actually lucky that the first one is, and we can treat the rest in terms of perturbation theory. So, and the final example is the family of these matrices which are closely related to Gegenbauer polynomials. And in the first example, we went like upside down. We were discretizing infinite operator. Now we are going downside up, and we are considering a family of operators for any n. We are pushing n to infinity, and actually the metric operators can be constructed in the same manner as before. We have printed just one, which is positive for sufficiently small a, and as long as you arrive to infinite dimensions, you can actually, it wasn't like the essential part of this talk, so I didn't include it, but you can prove essentially convergence to some Jacobi metrics, and the convergence implies the convergence of the resulting pseudospectra. And the pseudospectra are shown here for the first model, for the Robin square well, and here are for the Gegenbauer model. And now it's the first time you can look at the axis in the y direction, or in the imaginary direction, and you can see that the domain or the contour plot of the pseudospectra doesn't grow in any manner with the dimension, but the actual contour plot of the second model grows very fast, and that really means, what that means is that's actually a proof. It may be understood as a conclusive proof that the infinite dimensional matrix has not a bounded metric with a bounded inverse. This one actually has. in this case, I have not really considered any limit whatsoever. But it looks like the spectrum converges to some interval, and the pseudospectrum stays very nice. So this argument is just to emphasize the usefulness of using discretization methods in this kind of this branch of quantum mechanics. And the very last argument concerns that's actually the answer to question that was asked by Carl, which norm am I considering when plotting the pseudospectra of the cubic oscillator, which are running to infinity. So that means that if we combine the pseudospectral methods with the fact that we have our 3 Hilbert space framework, and we can essentially, at least in principle, in the case of imaginary cubic oscillator, it has not been proven. Essentially, it's the part of the work which is currently under consideration. But essentially, if we can prove the self-adjointness of imaginary cubic oscillator in any Hilbert space, then we can state that the space is physical, and the pseudospectra, as long as the operator is self-adjoint, have this form. And the pseudospectra which run to infinity have no physical meaning whatsoever. So we can rephrase the claims of the paper by Krejcíř and Tatar, and which says that pseudospectra actually they are not useless. They measure how the physical space is distorted, and if they are unbounded, it means that we could not return back to physical space by bounded metric with bounded inverse. So it is very useful concept which can be used to prove such a property. But as long as any operator should have properties of an observable, its pseudospectrum is really of this form. It's very trivial. So actually the imaginary cubic oscillator, there are essentially two possibilities. It has no physical interpretation whatsoever as an observable, or it has, and it is very trivial. And as a summary, well, what can I say? Just that we can really use pseudospectra to prove such kind of properties, and it should be really used in concerning Schrödinger operators with imaginary potentials. So thank you.
So there is still time for questions.
Okay, I have a comment from my work, from my own experience. So if you remember, in the first day I talked about the random diagonal with
I remember.
lower triangle,
Yeah.
lower diagonal greater than upper
Yeah,
diagonal.
I have actually seen the pseudospectra for this
Right,
model.
right. It's in Nick
Yeah.
Drifton's book, I think.
Yeah.
So I told you all guys that if I for numerical purposes I put it on a ring to make a periodic boundary condition. If I don't do it on a periodic boundary condition, then I can have a similarity transformation that maps it to permission problem. So all the eigenvalues will become real, but if you look into the pseudospectra, actually you see a problem.
Yeah.
So in that particular case, I can say that the pseudospectra is actually more physical than the real spectra. And so it's I think it really supports your.
Yeah.
Okay. Other questions? So if not, we are just on the end of the time. So thanks for speaking again.